This is Class 43, the last lecture of the semester for spring 2013. Since we're having this class electronically rather than in person, please submit your assignment under my office door by 5 o'clock on Friday the 3rd of May. And I'll do my best to grade that as quickly as possible, but chances are that it won't be graded in time for those of you who have your exam on Tuesday the 7th. And so in that case, I'd recommend that you make a photocopy of your assignment before you submit it if you're going to want access to it as you study for the final exam. So what we're going to be talking about today is an overview of hydrology, and included with that just some basic information about a hydraulic structure known as a culvert. So this is kind of a sneak peek of the types of topics that are discussed in Civil Engineering 433 if you choose to take that during the fall semester. Culverts, which convey water under roadways, are really important in the context of society and transportation, and particularly here in West Virginia, where so many of our important roadways follow along creeks that pass under the road, or rather the road passes over the creek. So culverts are pretty important, and we just touch on them briefly here in Civil Engineering 331, but in hydrologic engineering in 433 we actually get some pretty good software exposure to how to design culverts. What culverts are meant to do is pass water under roads and highways, and let's take a look at a video of a culvert failing. This is a culvert in Maine, which is meant to pass water underneath the road. What happened was that the soil surrounding the culvert eroded from the pressure of the headwater upstream of the culvert. You can see that trees and debris are actually being sucked under the road because at this point the culvert's beginning to fail. And not only is the main barrel of the culvert sort of rattling around loose underneath the roadway surface, but there's flow going around all the edges of the culvert. And so that dramatically increases the capacity to flow under the road when all of a sudden there's all this extra cross-sectional area. You can see that as a result of the soil that was around the culvert being swept away, that then the structural integrity of the road itself is threatened. Sort of like a slow failure, that nothing was really happening very quickly. But then all at once, something spectacular. Over the course of time that civil engineering structures usually fail, the structure will slowly rust, or the soil will very gradually settle. This is actually pretty spectacular to see it happening so quickly. So obviously this is a failure in the culvert. It should have been sized larger so that the water upstream of the culvert didn't pool so much. It was the pooling upstream of the culvert that and there's the pipe itself. So that gives you a sense for how large the barrel of the culvert was. Very big, and it's floating now because density is less than the water and it's floated to the surface. And now the road is closed, so pretty inconvenient for the people who are needing to travel on that, and that's why, that's a pretty good view there. Well, we'll talk about some of the factors that allow us to quantify the capacity of a culvert, how much flow can be expected through a culvert of any particular size. The flow rate can depend on how big the culvert is, its diameter, but also the length and slope of the culvert, depending on how the flow is through the culvert itself. There may be several different factors that govern or limit the capacity. And those include the material type that's used, the depth of the headwater, what's going on at the tailwater being downstream of the culvert, the channel that's receiving the flow that comes out of it. A culvert may be a rectangular box structure like this, which is made out of concrete. Also, this is looks like a rectangular box culvert, although quite a bit smaller than the one from the previous slide. In this case, you can see that the ground surface underneath the culvert is unlined. So although it may be masonry on the sides and there can be concrete reinforcing along the sides of the channel, in this case, if it was lined to begin with, that lining's been eroded and it's kind of an irregular surface now. In a lot of cases, the bottom of a culvert may just be natural materials like earth or clay. Here's a corrugated metal culvert. Here's another metal culvert, although this looks like a thick steel pipe rather than corrugated metal. And so failure can lead to the need for more highway construction. In some cases, they'll put in culverts just to avoid the cost and inconvenience of a dam. And so the culvert is quite a bit less costly than putting in a bridge over a stream. And what sort of flow rate to design a culvert for, how large to make it, is dictated by the size of storms that are expected in the area and how frequently you can tolerate failure. And the return period of a storm is characterized by how many years between, on average, a storm of a certain size would come through. And so a 10-year storm is one that has, in any given year, a 10% chance. So that means every 10 years, on average, you could expect the storm to come through. And so in 1 year, there's a 10% chance. A 25-year storm is a bigger storm than a 10-year storm because it's the size of storm that only comes around once every 25 years. And what that means is that in a given year, a 25-year storm has a 4% chance of occurring. The first step in analyzing a culvert is determining the flow that's going to have to be passed through the culvert and also the depth of the water downstream of it, so analyzing the tailwater. So you may be needing to find the normal depth of flow in the channel downstream to know whether the outlet of the culvert is going to be submerged or whether the water will be flowing out of the culvert and not bumping up against the submerged flow downstream. And the tailwater rating curve is what tells you for a certain flow rate how deep the flow is going to be in the channel downstream. And the software that I've referred to that we use in hydrologic engineering will automatically calculate the tailwater rating curve. And the tailwater rating curve sort of looks like this. If for a certain water elevation will correspond the depth that corresponds to a certain flow rate, so that you can know over a wide range of conditions what the depth of the tailwater is likely to be. This first case is showing how to calculate the flow rate through a culvert where both the headwater and the tailwater are submerging the entrance and outlet of the pipe culvert. So in this case, since it's really flowing as a pipe that's full, the way that we would calculate the flow rate is by using Manning's equation. You can see that the n value in here is used to determine the energy loss through the pipe section. And the driving force, the delta H, the height difference between the headwater and the tailwater, that's really what's causing the flow to move from 1 towards, in this case it's saying location 3. Water is moving from left to right here because of the difference in water elevation between the headwater and the tailwater. And so that's the driving force, and you can find out the flow rate as a function of the cross-sectional area, the energy loss due to pipe friction, and then there are also entrance and exit losses. So this 1 is an exit loss coefficient. The K sub E, usually in our book it mentions that you can, with a little bit of care, get the entrance losses down to maybe 0.1, and so the sum of the exit and the entrance loss would be 1.1. Since Manning's equation isn't really accurate in characterizing pressurized pipe flow, sometimes they don't bother to put all the sophistication and complexity of this equation into assessing the flow capacity in type 1, which is inlet and outlet submerged. And so sometimes Manning's equation is just simplified to some energy loss coefficient times the cross-sectional area and then square root of 2GH. And H is the difference between the headwater and the tailwater. The depth, the criteria that we say the tailwater is fully submerging the outlet is that if the critical depth plus the diameter divided by 2, so the average of the pipe diameter and the critical depth divided by 2, that is known as a control depth. So if it's any deeper than that, then the tailwater is going to control flow, and then that's when type 1 situations are applicable. Type 2 is when the water depth isn't quite as high as fully immersing the outlet. Again, there is some delta H that's the driving force between what's getting the water through that pipe. The water is fully submerged. The water surface is all the way to the top of the pipe as it flows through the pipe. It's just that when it exits from the pipe, it's the capacity of the channel isn't fully submerging the outlet. It's not going above the crown of the culvert, the crown being this top section right here. In culvert terminology, invert is the name of the bottom part of the pipe, and crown is the top part of the pipe. So we can again use Manning's equation to estimate the effect of the head loss through the pipe, and the driving force is the difference in the elevation. Here's some typical N values that are used in culvert design and analysis for some pipes that we haven't seen in the closed conduit or in the channelized flow. For example, corrugated pipes would be uncommon in most applications except for culverts. Type 3 is when the water isn't flowing all the way up to the surface, the top crown of the culvert. So what's limiting how much water can get through the culvert is the orifice. And so you can see that this opening, once the water gets through the opening, then the normal depth through the culvert is less than the barrel height. And when that's the case, then we calculate the flow capacity of the culvert simply just to be the flow rate times an energy loss coefficient, the area, square root of 2GH. Now here H is the distance from the water surface down to the centroid of the opening of the culvert. So this is the orifice equation. Alright, so that's just some brief overview about culverts, and what we'll take a look at next is some information related to hydrology. And hydrology is the study of the movement of water through the environment. And this slide illustrates the water cycle, and it shows that what drives the hydrologic cycle, or the water cycle, is the sun. And the sun causes water to evaporate from the ocean, and moisture that's evaporated from the ocean will condense onto particles of dust that are in the atmosphere into clouds, and although much of the rainfall that comes from the atmosphere falls just back onto the ocean because the ocean is the majority of the Earth's surface, some of that precipitation falls onto the Earth's surface. Some of it may fall into areas that are really grassy and good for infiltration. Steeper surfaces or surfaces that don't have vegetation to help aid in infiltration may lead to more surface runoff. You can see that precipitation can take the form of liquid rain, or it can be snow that falls, and snow is different from rain in terms of how much runoff occurs, because before water that falls onto the surface will turn to runoff, it has to thaw, and that's generally a much slower process than just the liquid rainfall getting onto the surface and then flowing because of gravity. There are divisions within hydrology. The surface hydrology is focused more on the flow and movement of water above the ground level, and subsurface hydrology would be the study of water's movement through and underneath the soil surface. A big part of the hydrologic engineer's focus is understanding the relationship between rainfall, how much rainfall there's likely to be in an area, how often storms of certain sizes will come through. So that would be both the temporal and the spatial distribution of precipitation. The study of infiltration, to know what fraction of the precipitation gets into the soil versus what fraction of it will run off. These are three big areas where studying how much rain occurs is a statistical exercise that takes into account rain gauges that are spread all across the country, and there can be estimations of precipitation made from radar information. Infiltration, how quickly water gets into the soil, depends on the vegetative cover, the land use of an area. For example, whether soil is paved with an asphalt or concrete versus if it has a grass on it, obviously it's going to have a huge impact on how much water infiltrates, and then therefore will have an impact on how much runoff occurs. Some of the way that the rainfall distribution is characterized, there can be electronic devices like a tipping bucket that has a certain volume, and with a tipping bucket usually water will fall into the rain gauge, and then when a certain volume of water accumulates, it will cause the tipping bucket to turn over, and how often a certain small volume is activated to dump itself out would allow you to have a pretty good sense for the temporal distribution of the rainfall. So in a rainstorm, maybe the tipping bucket is emptying itself every 5 minutes, then you'd know with very high resolution what the intensity of the storm was all through the duration of that storm. Whereas a more common rainfall gauge, which is just a period average type of a gauge, a certain volume is looked at. You look at a gauge every day, and so in a case like this, you'd only know the rainfall depth over a 24-hour period rather than the intensity at much more frequent intervals that can be obtained with electronic devices. It's a little bit confusing for students sometimes to think of rainfall quantities as a length. And so on the news, when they say there was an inch of rain, obviously what they're saying is there was a certain area that had rainfall, and the rainfall depth was 1 inch, or 2.54 centimeters, or 25.4 millimeters. And so you can find the volume of rainfall that occurs by multiplying the area over which rainfall fell and then the average depth. So that would give you a certain volume. Recurrence interval, as we talked about with culverts, the fact that a high-intensity storm is rare, and so in any given year it has a low probability of occurring. And so sometimes we refer to storms by their infrequency of return. So a 10-year storm, a 20-year storm, a 50-year storm, and so on. Here is a map that illustrates the concept of spatial distribution, and it's showing the depth that will be observed in a 10-year, 1-hour storm. And so if we look down in Miami, just as an example, in Miami they may experience 3.8 inches of rain in a 1-hour interval. a storm that's lasting for 1 hour, 3.8 inches could accumulate during that 1 hour, but a storm that size would only come through once every 10 years. Now the intensity is much lower in the western United States. A 1 hour storm may only drop 0.6 inches of rain in much of Nevada, for example. And so there's a broad distribution of rainfall depths and intensities across the United States. Some of these graphs show the concept of temporal distribution, and we'll talk about this one first. This is a typical 24-hour storm, and different parts of the country are broken up into different zones. Here in West Virginia, for example, we're in Zone 2. And so what this figure is showing is that during a 24-hour storm, the precipitation on average will be relatively slow at first, and then there will be some period middle of the storm where the intensity is very high. So this line being very steep indicates that a big depth per unit of time is being experienced, and then as the slope decreases again, that means that it's just sprinkling for the rest of the 24-hour period. So in some parts of the country there really isn't quite as steep a location. This type 1A storm isn't ever as steep as we can sometimes see in Zone 2 or in Zone 3. So temporal distribution is talking about the distribution of rainfall during the rainfall event's time. And sometimes to simplify the intensity of rainfall, we'll use this triangular distribution. We may assume that there's some rainfall intensity, and the amount of time it takes to get to the peak would be called T sub P, and then there's this total duration of the storm as it tapers off down to back down to zero. This figure is called an intensity duration frequency curve, and there's a precipitation data frequency server on the National Atmospheric and Oceanic Administration's website. NOAA has a website where you can click anywhere on the Earth's surface, anywhere in the United States, and it'll generate a curve that tells you for a certain storm duration and a certain return period what the intensity of storm is likely to be. And so just to give you an illustration, if this was okay, so this is saying it's for Newark, New Jersey. A storm that is 60 minutes long is going to have, for a 5-year return period, an intensity of about 1.6 inches. But a 60-minute storm that's coming around once every 100 years would have an intensity of about 2.7 inches. And so these are very useful in estimating the volumes of runoff that may accumulate due to a storm. We use IDF curves like this quite a bit in hydrology for designing the flow rate that may need to be passed through a culvert, for example. All right, now just a brief overview of infiltration and some of the factors that affect that. Water will enter the rain will fall onto the surface, and infiltration occurs at a greater rate if there are certain soil conditions. A sandy soil will infiltrate more water than a clay soil, for example. So one of the factors that plays into the rate of infiltration is the soil type. And you can see here that there's a water table, and below this water table the soil pores are saturated. Above the water table and there are voids that aren't saturated, and there may be moisture in the soil, but it would maybe be adhering to soil grains and not filling the entirety of the voids in the soil grains there. And so water will move from high head towards low head, and groundwater flow into a stream or into a lake is called base flow. And so we have to know about the movement of water because it is going to contribute to flows and streams. So we've talked about how soil surface like concrete or vegetative type can affect the rate of infiltration. And the soil itself has properties like its hydraulic conductivity, which I'm sure you've heard about in your soils class, and the porosity of the soil. All of these factors come into influencing the rate of infiltration. And unsaturated flow is what we sometimes are most interested in, because whether or not these voids above where the water table normally is are filling up with rainwater can have an effect on the rate that infiltration occurs. So we have to keep track of how much soil moisture is in this vadose zone, as it's called, the zone of aeration above the water table. This illustration just shows that underneath the Earth's surface there's a zone of aeration where there is moisture in the soil here, but it's not fully saturating all of the openings in the soil pores. And so the capillary zone is where water is sort of wicking up from the water table, and underneath the water table all of the openings between soil grains are full with liquid, but in the capillary zone there's a little bit more moisture than there ordinarily would be in the intermediate zone, because it's wicking up from the aquifer. And this is showing in the graph here is showing as you go up from the water table, theta sub S is the fully saturated water content, and the water content decreases the further away you get from the aquifer surface. And we'll talk about this in a lot more detail in hydrology if you choose to take that class. There are some models that we use to describe the water content that can be observed and the rate of infiltration. I didn't want to get into too much detail, just illustrate that these are some of the concepts that come into play.